Good afternoon, everybody. Good afternoon, everybody. How's Ignite going? Pretty good? Best Ignite in Orlando this year so far? Welcome to Inside Microsoft Azure Data Center Hardware and Software Architecture. My name is Mark Russinovich. I'm the Chief Technology Officer of Azure. I've been in Azure for 7 years. It's been a fun ride. I think it was 2012, TechEd Orlando is when I gave my first Windows Azure internals talk, and about 50 people showed up, which was exciting. It looks like there's some more interest now in Azure these days, which is also very exciting. What I've got today is 75 minutes of tightly packed, dense material where I want to give you a look underneath the hood of our data center architecture across network, compute, storage, our server designs, and our data centers. Given the short amount of time, I'm going to kind of skim through these things and highlight places where their architecture is differentiated, and also talk a little bit about some of the things that we're doing for the future. So I'm going to give you a look at some future technologies that we haven't deployed yet, but that we're working on and show a lot of promise. Here's the agenda. I'll start with a look at the physical data center architecture and the way that we lay out data centers across the world. Then I'll dig in to the physical networking aspects of how we connect our data centers together and how across the world and within a region. I'll take a look at logical network architecture, the different components that work together to implement networking. Then talk about our servers, the kinds of server generations we've been deploying in Azure. Talk about our compute architecture and show you some innovations that we've got in the compute services. Go inside of storage. I'll talk about some cool new storage technologies we're working on. And then finally, I'll conclude with a look at the OS that we run underneath our virtual machines inside the data center. So let's start with a look at the data centers. And first, to understand our data center architecture, you got to understand the way that we approach laying out regions across the world. The first thing we do is define what we call a geography or a geo. As you know, Western Europe is considered a geo. The United States is considered a geo. More and more what you're seeing us define as a geo is actually a country. So while we have Western Europe, and that serves a lot of Western Europe business, we also define a geo as France, and we define a geo as South Africa that are very country-specific. Germany is a special example because we don't operate that geo ourselves. We use a third-party T-Systems to operate it on our behalf, which is something that German businesses and the German government like from a perspective of data sovereignty, data privacy. Within a geo, this is unique to us as far as the large public clouds. We go into every geo with at least 2 regions. We define what's called a region pair. And that region pair is something that is backed up with the way that our software that supports geo-replication are connected with one another. It also is backed up with the way that we roll out software. The idea behind region pairs is that you can build a disaster recovery solution on top of us without having to take your data outside of the geo. So for example, in Germany, we've got 2 regions. And so you can build a DR solution and still adhere to the data sovereignty requirements that you've got in Germany. We want those regions that are paired together to be able to independently survive large-scale physical disasters like a hurricane, if that was to hit a region. And so that typically means that they're several hundred miles apart on different tectonic plates and different electric grids, different large floodplains. And that means that you've got a latency of replication typically good for non-zero RPO, or return point of operation, meaning you might lose some data if you fail over from one region to another, but it still gives you a DR capability. What we've introduced, just on Friday we announced a preview of availability zones. Availability zones are what we'd go do within a region to provide resiliency against data center localized faults. So with availability zones, we go into a region with at least 3. This is something that we've got as a policy, and we do 3 because services that use quorum-based replication to store data durably need to have an odd number so that you can vote on when data is durable. And you'll be able to tolerate an AZ failure and still have your data persist. So within a region that has AZs, and we're launching with 2 initially, US East 2 and West Europe, which is Amsterdam. You'll be able to stripe your services across the AZs or create independent deployments of your services such that you can tolerate an AZ failure in the face of a flood, electric problem to the data center, a networking problem to the data center. We are taking the approach where we define physical AZs and then we lay on top of those logical AZs that map to particular subscription. This allows us flexibility on the capacity management of the physical data centers that comprise AZs. So for example, here you see subscription 1, its views of logical AZs maps to a subset of those physical AZs, whereas subscription 2 might have a different logical mapping. Like I said, we're going out with 2 geos, and by the end of the year, we'll be launching our French regions. One of those, Central France, which is based in Paris, around Paris. You can see there the layout of the regions that we've got and the distance between them. Because the AZs, we shoot for less than 600 microseconds within the AZs, and we shoot for less than 2 milliseconds latency within a region. That means we've got a latency envelope on how broadly apart those data centers that make up AZs can be, typically tens of kilometers apart. And you can see that we've got that structure here in central France. As far as our data center security, we follow all the strict best practices around physical security in our data centers, including the fact that to even get access to the site, you've got to go through a well-defined access point. There's gates, there's fences, there's cameras monitoring 24/7. There's a security team that is monitoring the cameras 24/7. They're also doing spot checks and random walkthroughs to the data centers. Once you get into the data center, you get access only to the part of the data center, the colo facility that you've got permission to get to based on what you're supposed to do. You can see that there's metal detectors on the way through. And we also make sure that only approved devices that can store data make their way into the data center so that we don't risk data leaving the data center without our knowledge. As far as the physical design of our data centers, we've been continuously improving the PUE of our data centers, making them more efficient. We've also have a big commitment to green energy. So since 2012, Microsoft has been carbon neutral with our data centers. And you can see that by 2018, next year, we plan on having 50% of our energy come from renewable resources. 60% by 2020, and our long-term North Star goal is to have 100%, of course. As far as the different kinds of renewable energy we use, you can see here a variety of different types. For example, in our Virginia data center, we're using a lot of solar. We're using wind power in Texas. Turns out it's pretty windy in Texas. We're using local renewables in Wyoming. So we're actually using biodegradable fuel sources to power a certain amount of the data centers there, wind power in Illinois, and clean energy in Kansas. We're also working on new technologies that are breakthrough technologies in terms of powering the data center. This is fuel cell technology here. You can see this is a prototype. We've run a pilot, and we're about to run in a lab, and we're about to run a pilot in our data centers of this new fuel cell technology that replaces generators. It's about double as efficient in terms of delivering energy from the outside into a server. And here's an example of one of those fuel cells opened up. This serves 10 kilowatts of power out of that fuel cell right there. And this is going to cut our costs as well as make our data centers much more efficient. Now, to show you what our data centers are looking like these days, here's some screenshots of a data center. This is our Quincy, Washington's facility. You can see we're doing massive build-outs, of course, everywhere as we go into regions and expand. Those are all data center colos that are serving Azure customers. You can see here's another view of it from a different angle. Here's Cheyenne, Wyoming. Anybody guess what country this is in? There's a hint. And if you're from that country, you can't guess. The Netherlands, right. How did you know it was the Netherlands? Why? Because what? It's flat? Well, there's lots of places that are flat. No, the clue is that building at the top. Anybody know what that is? It's actually not a data center. Now, it is the Netherlands. So it's a greenhouse, right? It's the Netherlands. It's a greenhouse for one of two things. I'm not sure which one it is. But this is our, so that's, Amsterdam, the Netherlands. Here's a look inside one of our data centers. This is one of our newest data centers. This is a screenshot from a hallway in Cheyenne, Wyoming data center. And by the way, you heard a lot about quantum computing. I couldn't actually bring you a picture of a quantum computer, so I mocked one up with Legos. And you can see that I followed all the data center best practices, renewable energy, windmill. So there's a subsea cable that goes through the coffee cup right there for connectivity to the outside world. Just-in-time access control there with two-factor authentication. And then we've got a backup plan when we run out of physical space to create data centers in Minecraft. That's our first proof of concept there, Minecraft US East 1. All right, so let's take a look inside the physical network between these data centers. And we've got a massive worldwide optical backbone. We've got something called SWAN, which is what we use to shape traffic between our data centers and route traffic around problems, reduce congestion. And then we also have something new that we've been rolling out this year called Regional Network Gateway. So I'll take you a look inside those things, starting with our indoor data center dark fiber backbone. This is a map of the world showing Microsoft dark fiber. We have over 30,000 miles of dark fiber connecting our data centers. When you enter one of our data centers with your network traffic and then talk to someplace else in Azure, you're staying over our dark fiber. So if you come in through ExpressRoute and you come out, for example, in California, and then come out in Amsterdam, you're staying over our dark fiber the whole way through. We've got 4,500 peering points. We've got 130 edge locations as well, which we continue to build out, which only a subset of those are shown on this map. How many people heard about the Maria cable that just went online last Friday? So this is a subsea cable that we started laying a little over a year ago. It's a joint project between Facebook, Telsus, and Microsoft, and it is the first subsea cable that connects between the United States and Europe in a different place, different connection points other than New York to England. This one goes from Bilbao, Spain to Virginia. And the reason that we wanted to create this other route is when Hurricane Sandy hit, us and Facebook both realized we had a huge dependency on those connections into New York. And so we wanted another backup cable. So this cable that went online is the highest bandwidth cable across the Atlantic. It's 160 terabits. It's 4,500 miles long. So this was quite a big capital expense, but it just gives you an example of the kind of money that we're throwing at building the best network connecting our data centers in the world. Here's a look at digging the trenches at the connection points. Here's the path that cable follows from Spain to the United States. Oh, actually, that's on this slide right here. That previous one is showing some of our Pacific cables that we've laid. Now, let me talk a little bit about the RNG, the Regional Network Gateway architecture. As one of the things we realized a few years ago as we're building out these massive regions with multiple data centers, that we were running into constraints on how efficiently, meaning with the fewest network devices with high availability and low latency and high bandwidth between our data centers. And so we started this project called Regional Network Gateway, which is built on 100 gigabit network optics. It's designed to be fully modular and expandable. Now, the regional network gateways go into their own data center facilities. You can see that we've got multiple RNG to serve as backups from each other. They're in different data centers. The traffic from the data centers routes through both of them. So if we lose an RNG, that we've got enough bandwidth in the other one to handle the traffic out to the backbone. We support deploying these in small, medium, and large T-shirt sizes to support the size of the region, meaning the number of data centers that we've got in the region and the amount of bandwidth that they require, so that we can quickly expand capacity in a region as we expand. One of the big breakthroughs that we've been making is in the area of network optics connecting data centers together. So this is a project called Madison that we started a few years ago. In fact, the idea came from it in 2014 as we realized the cost of network optics connecting data centers together was a significant chunk of the overall expense of a data center's connection, a data center including its connection to the outside world. So to get ahead of the costs, we started going with ultra low cost, low power optics that directly connect data centers together through high bandwidth optical connections with, again, a very expandable architecture. So you can see that we've got those RNG hubs. They're connected through Madison network optics to our data centers using that. Here's an example of the 100G colored QSFP28 network optic connection. And just to give you an idea of just how much more efficient this is than a traditional architecture, on the left side, you can see it's a traditional architecture with coherent optics. On the very left rack there, that's 3 T2 network switches, T2 meaning tier 2 in the data center topology. Tier 2s are what connects to other data centers within a region in the outside world. Those next two racks show you 8 terabits per second fiber pairs on both those racks using traditional network optic devices. To power to support a 32 megawatt data center with the bandwidth that we want configured for that data center, you would need 16 of these lined up side by side. On the right side, you can see that this is what Madison looks like. It's a few U's in a rack, 4 terabits per fiber pair. You need 32 of these to support a 32 megawatt region, which fits in 2 racks by itself. So 16 times 2 on the left, and then 2 racks on the right, and a fraction of the power, because each one of these is 500 watts. So that's an example of kind of the optical breakthroughs that we're making in Azure. That's a look at our physical network, and let's dive in and take a look at the logical side of it. Our data center networks are built on the fundamental premise of software-defined networking. We were doing software-defined networking before people could start a software-defined networking company and sell it for $1 billion. Azure was already building software-defined networking into our data centers. The idea behind software-defined networking is that you take the old appliance that had all of the network layers built into it, from the control plane, the management plane, and the data plane, and split those off into software-defined components that can be scaled independently, and you can build high availability into them very easily just by building highly available software. And that's exactly what we've done in Azure. An example of a management plane operation is creating a tenant or creating a deployment of virtual machines or virtual network. Example of what the controller would do is take the ACLs that you set on your virtual network and send those down to the switches, and that's where the data plane is operating at the switch level as software-defined switches, where it would apply the ACLs directly at the host on the server, where those virtual machines that are connected to that virtual network talk through. And so we have the ACLs right there on the host. The idea is push as much down to the host as we can and have this scalable software architecture above that. Here's a look at the overall Azure architecture. You can see the Azure Fabric controller there in the middle. That is what's managing all of the VMs in our cloud, as well as our physical server deployments. You can see a hardware manager underneath that, which manages the health of the hardware and provisioning of the hardware on top of the server infrastructure. And then above that, you have microservice orchestrators that deploy into the virtual machines. You have Azure Resource Manager as the universal control plane for Azure, and then you have different interfaces that can talk to Azure. If we focus directly in on networking, Azure Resource Manager has this concept of resource providers. They define the resource types that we support in Azure. And a resource type could be a database, it could be a website, it could be a virtual network, it could be a load balancer, an IP address. In the case of networking, there's a network resource provider that provides those resource type definitions to Azure Resource Manager for you to talk to on the management plane. Beneath the network RP is the regional network manager, which manages resources at the region level. And you can see there's a network state manager, a directory service, which is the virtual network definition directory. The network RP works in collaboration with the compute RP, the resource provider that defines a virtual machine, so that when you define a virtual network and attach it to a virtual machine, those two work together to rendezvous on a server through something called the node agent and the network agents there. The network agents there would do things like manage the load balancers, manage the virtual network. And then there's a virtual filtering platform that I'll talk about in a few minutes. That is actually where all the rules are enforced on routing and ACLing. One of the kind of innovations that we're making with virtual networking is supporting keeping services off the public internet. And so one of the big asks that we've gotten from a lot of financial customers is keep services off the internet and make it so that those service endpoints that I talk to are only accessible from a specific virtual network. So we've just introduced into preview this week something called virtual network service endpoints. So this is the kind of defensive depth, keeping your stuff off the internet. The first resources we're supporting with this are storage accounts and Azure database, but you're going to see this sweep through all of Azure services. Over the next 12 months or so, you're going to see them start with more of the core services and then spread out from there. The idea is that we will universally support this capability across our PaaS services. Here's an example of storage account A and a virtual network that you want to be able to talk to it, and another virtual network you don't want to be able to talk to it. You set an ACL on that saying only VNet A, specifically a subnet of VNet A, can talk to that storage account. And now access from the internet's blocked, access from virtual network B is blocked, only A can get through. And I've got a little demo here to show you of that in action. So here's Azure portal, and I'm going to click on this storage account here. I'm going to go to firewalls and virtual network, and I've configured this storage account such that only subnet 1 from VNet 1 can access it. Any other VNet that tries to access the storage account will get access denied. And we can go take a look at the effective routes for network adapters that are attached to different subnets and different VNets and see that those themselves don't have access to it. So here you can see that the effective routes for this NIC, which would be we would attach to a virtual network, to a virtual machine, it does have access to that virtual network service endpoint that's defined on top of the storage account, but this other one, which is not part of that subnet, doesn't have that in its routes. And if I go take a look at the behavior that we'll see, this is the standard off-the-shelf Azure Storage Explorer. This is running from the virtual network, virtual machine that is not joined to the authorized virtual network. And when we try to test access to that account, we get a forbidden. So we're not allowed access. On the other hand, if I switch to this other VM and add that storage account to the Storage Explorer, you can see that I can access it no problem. So this is VM1 that's attached to that NIC1 with the effective route on its NIC that gave it access to that storage account. So that's a look at how we're innovating in the space of logical networking. I mentioned that we try to push as much down to the host or the server as possible. One of the challenges we've had is that as we push more logic into the servers, specifically the rules on routing and load balancing and ACLing, the amount of CPU we spend processing those rules goes up as the bandwidth goes up, as the number of packets that flow through go up. And we've gone from 1 gigabit networks when Azure started to 10 gigabit. We're at 40 gigabit now, and we're soon going to go to 50 gigabit off our servers. When you start to talk about 40 gigabits and start to talk about processing rules on that kind of traffic, you're burning a lot of CPU cores. What we like to do is save those CPU cores for actually processing customers' virtual machines, giving them to you so that you can use them, instead of burning them on this kind of processing. So a few years ago, we realized that by using field programmable gate arrays, FPGAs, which I'll describe in a second, we could offload all of that processing from the CPU onto these devices. Now, what is an FPGA? Well, the name kind of reveals what it does. You can reprogram. It's like hardware you can reprogram. So it's not quite as fast as ASICs or custom silicon, but it's way more efficient at specific algorithms you can program into it than general purpose CPUs or GPUs. And so what we've done is taken that core networking stack, the rules engine that runs on the servers, that virtual filtering platform, and program that into our FPGAs. Then what we do is surface through SRIOV network adapters into the virtual machines such that the virtual machine can effectively talk directly to the network because these FPGAs are in line with the NIC on the server. So every byte that comes into the server and goes out goes through this FPGA for processing. What that gives us is the fastest network in the public cloud. And I'm going to demonstrate that. But these FPGAs is part of a larger effort of ours to have this reprogrammable logic be an essential part of our data center infrastructure and support other things. Now, the reason why we just didn't go do ASICs is because our software-defined networking continues to evolve. And when you go to make an ASIC, you're basically making at least a year commitment to 2 years from the time you decide you want to do something to the time you actually have the ASICs and can put it in production. And then you typically want to get a few years of life out of those. Well, today in the public cloud, a few years is eternity, and our software-defined networking stack, we don't see any end in sight into that evolving. And so this gives us this flexibility of getting high performance without getting locked into a design. We update this typically every few weeks with enhancements. And let's go take a look at the comparison between traditional, which is you go through the virtual switch on the CPUs into the NIC, versus the FPGA acceleration on the right side, where the CPUs are completely bypassed. I'm going to show you a quick demo here of just how dramatic that is, because besides saving CPU, we also save on network latency and can achieve close to native network bandwidth off the network adapters. So let me go to this VM here. Now, I've got 2 VMs that are going to talk to each other through the standard non-accelerated networking paths, and 2 VMs that are going to talk to each other through the accelerated networking paths. I'm going to show you the difference in bandwidth as well as the difference in latency between these 2. And I'm experiencing a little bit of lag here, so looks like the conference center is not using accelerated networking. Yeah, and so for some reason, this is not responding. Well, let me try, see if that is responding. That one is. Oh, here we go. So this iPerf server on one side, this is a little tool that will test network bandwidth, and iPerf client over here. And if I go back, I've got a network bandwidth monitor here. And we're going to see this thing achieve roughly, you can see, 600 megabytes per second. So okay, but not anything to write home about. Now on this side, the accelerated VM, here's the accelerated VM server, here's the accelerated VM client, the same test. And you can see I'm achieving between 20 and 25 gigabits per second, which is about as high as the line speed on that network adapter will go. So close to native bandwidth off the accelerated networking FPGAs. And then if we want to take a look at what the latency looks like between VMs, let's take a look at that. Here's another tool called QPerf, which is aimed at measuring bandwidth, latency. So here's the QPerf client. And what's going to pop out of this is a 10-second run, is the average network latency per packet sent from one of the VMs to the other VMs. And you can see it's about 150 microseconds. So you typically experience somewhere between 110 and 140 microseconds of latency. If we go to the accelerated network VMs and try the same tool test, and I'm experiencing the lag here now. Okay, hold on, it'll catch up hopefully. Yeah, here we go. And let's take a look at the bandwidth, or sorry, I'm not looking at the bandwidth, I'm looking at the latency here. We're going to see the latency for accelerated networking. And you can see 30 microseconds. So over 1/3 reduced latency, because basically the VM is essentially talking directly to the physical network in the data center using those FPGAs. So that's a look at our accelerated network and our physical network. Let's take a look inside of our servers now. How are we deploying servers, and what kinds of servers do we have in our data center? So I'm going to show you kind of a walk through the golden oldies here, starting with the first server that we launched into production. And that's what we called the Generation 2 server. It had a 1 gigabit network adapter, like I told you. It had 32 gigabytes of RAM. This was considered a reasonable size server back in the 2010 timeframe when Azure launched. We've been increasing the capacity and size of our servers every year because, of course, the more VMs we can pack on a server, kind of the more amortized the cost of the base cost of having just a server in the data center occupying space and power and networking is. So you can see our Gen 3, one of the things we started to add in our Gen 3s is a bunch of SSD. And you can use that SSD either as local storage on some of our VM types or as cache for remote storage in our S line of VMs in each family. We also have introduced HPC servers. The difference between these and the general purpose compute servers is not so much that they have different processor characteristics. Of course, these are processors that are optimized for HPC workloads, but the fact that they have their own network in these clusters, 40 gigabit InfiniBand network. So you can get even sub 2 to 3 microsecond latencies between those virtual machines, which is great for MPI type workloads. Here's our Gen 4, and by the way, you probably noticed on the top, the relationship in RAM is shown vertically between the server generations, and the relationship in cores is shown as the width of those columns between servers. You can see that I had to reset because we introduced a server we called Codzilla internally. When we launched this, it was the largest server in the public cloud. We had our G5 and GS5 VM types, which support close to 500 gigabytes of RAM on them. That sounds pretty beefy. Well, here's our Gen 5.1. Here's our GPU Gen 5. So we started to introduce GPUs for visualization and for compute. And then we just introduced this. This is we call it the beast. And this is what supports our M-type virtual machines. So this thing has 120 cores on it, has 4 terabytes of RAM on it. So this is, and it's got a lot of SSD, a ton of SSD on there. So this is really kind of aimed at scale-up workloads, specifically SAP HANA and SQL and those kinds of databases that like to have a lot of in-memory processing. Finally, we're rolling out our Gen 6 line now. So this is what our Gen 6 looks like. You can see it doesn't have quite as much RAM as our Gen 5. We've actually more optimized the RAM per core ratio to suit the kind of compute workloads that we see in the general fleet. And so that is represented with our Gen 6 design. Now, our Gen 6 design is the first design that's rolling out based on server and rack design we called Project Olympus. This is a project that we've actually contributed to the Open Compute project. And we sought feedback from the outside world, contributions, pull requests effectively, to shape the design of our servers. This is open design, meaning any OEM or ODM can go and take that design and build these kinds of servers and racks. And it was designed with the current state-of-the-art servers and data center topology. You can see there, it's designed to support 50 gigabit networking. It's designed to support FPGAs, high-density hard disks, M.2, SSDs, high-density GPUs, the processors from Intel AMD, as well as ARM64, and it's got battery-backed RAM, or NVDIMM, in it as well. We are also introducing high-density SKUs for GPU, or deep learning. This is one of the things, you hear about our focus on AI and ML. Well, training is done on GPUs, and the current state-of-the-art for training GPUs is GPUs that are wired together using technologies. This is NVIDIA GPUs that we've got, and they're wired together using NVLink, very high bandwidth buses that connect those GPUs together. We'll have 8 GPUs in a server, and you can wire these things together to achieve a total cluster of 32 GPUs together with this low latency network links. As far as the physical security of our servers, we've designed a custom ASIC that's NIST compliant. This is designed to enforce pre-boot integrity, boot integrity, and then runtime integrity of all the firmware components in our servers. So it's designed to get attestation of the firmware running on each component, and then roll that up into serve as a root of trust that can basically attest to the health according to the policies for firmware that we've got on those servers. Here's a picture of, it's a microcontroller there. You can see right there on an add-on board. This thing sits on SPI and QSPI buses so that it can look at everything from the BMC to the firmware on the network adapters and measure them and then test them and create hierarchical chains. So anything that's even on a bus, the devices that are on that bus can report and attest through that bus up into the Cerberus root of trust device. And this is also tamper-proof, of course. And we're working with NIST and defining open standards around what we design here for the Cerberus firmware. Also, when it comes to server technologies, I talked a little bit about FPGAs in the context of accelerating infrastructure. Accelerating networking, we're going to be accelerating storage with our FPGAs, basically giving VMs direct access to local storage devices. But the other place we use FPGAs is for machine learning. And a couple weeks ago, about 3 weeks ago, we announced at Hot Chips, an academic conference, a new project that we've been working on called Project Brainwave, which is using FPGAs to accelerate deep learning inference, where you can take DNN models, we'll process them into intermediate language, and then we'll decompose parts of it to run on CPUs and parts to run on FPGAs. Those FPGAs, you can see, support, basically, they're connected on the network, and we can take layers of the DNN and put them on different FPGAs that are wired together directly on the network so the data flows can go right through the layers without touching a CPU. What this enables us is to get massive bandwidth, basically almost peak bandwidth out of these devices with extremely low latency. And so I've got an example that shows you the traditional DPUs or DNN processing unit approach, which is batch-oriented, with what Brainwave delivers, which we call real-time AI because it is so low latency and it's so efficient that you can literally have a batch size of one request, basically saying, what is this? Is this a cat? And instead of saying, here, I've got 128 cats or images, which ones of these are cats? So let me run that real quick for you. A little GUI that we've got here to show you side by side a comparison. So what I'm going to show you first is something you would see on GPUs or custom ASICs from other companies that have come out. The kind of bandwidth that you get when you've got big batch sizes, 256 you can see there, requests for inference. And so you're driving quite a bit of bandwidth, but once you start to reduce the batch size, you can see that the bandwidth on the device goes down, continues to drop. So you're basically wasting a whole lot of the processing power of those devices because they're really designed for batch processing of these inference requests. By contrast, if you take a look at Brainwave, there it is with, and this is running on a machine with the Stratix 10 FPGA. Stratix 10 comes from Intel. These are the FPGAs we'll be deploying for deep learning. And you can see that even at batch size of 1, as we go over the right size, we're pushing 40 teraflops. The peak capacity on these Stratix 10s is around 80 or 90 teraflops, so we've still got some headroom to get some more efficiencies out of it, but you can see that we're driving more efficiency, more bandwidth than you can off these batch-oriented systems. And on top of that, if you take a look at the latencies that we're experiencing at that batch size, so this is taking a log of the latencies. Here's the DPU batch size. So that's 65.81 for a batch size of 1 off of the traditional batch-oriented system. And then if you take a look at what we're getting off of the Brainwave, it's less than a millisecond. Hence, we call it real-time AI. Basically, you can just send this thing inference requests and get responses back in real time, even at batch size of 1. So that's a look at Brainwave. Now let's take a look inside of the Azure compute stack. So I've gone, taken a look at data centers, physical networking, logical networking, servers. Now let's switch over into compute. And this is the architecture slide that I showed you earlier. What I'm going to be doing is focusing on the compute parts of it. So basically, Azure Resource Manager and the Fabric Controller on down. And let's take a look at what that looks like. So we've got one service that is a geo service. It's a global scale service. That has Azure Resource Manager. The reason we decided to make it geo scale is because this thing can be weakly consistent, and that allows it to survive failures of any one particular region, and gives you the convenience of not having to go to our portal and say, oh, show me the stuff I've got in US East 2. Show me the stuff now let me switch my context over to Europe West. You can see your resources across all of Azure because Azure Resource Manager is a globally deployed service. Now, underneath it, though, for high availability and resiliency of particular resource types, because when you go deploy a resource in Azure, you say which region you want it in. You say, I want the storage account in US West. I want this VM over in US East 2. Underneath there, we've got all of our resource providers are regional in nature. So you can see compute resource provider, network resource provider, regional network manager, regional directory service, and the USLB, software load balancer. Those are all regional services such that failure and impact to one region doesn't affect the services in another region. Beneath that, we decompose into clusters. So this is another way to reduce blast radius and to scale, is to slice these things into layers, and then we have something that works at cluster layer. Clusters are typically in the compute world anywhere between 1,000 and 3,000 servers. And then down on the nodes, we've got agents that support these higher level services, just like you saw in the SDN stack. We've got basically the same layering in the compute stack as well. Now, as far as how these things work together, I mentioned earlier that they orchestrate with one another, and that's kind of the orchestration you see between these things. So we're going to spend the rest of the session talking about each of these lines, which I think you'll find fascinating. All right, you don't seem too excited, so maybe we'll skip that. Just to drill into CRP, all of our services are microservice based. And most of our services are built on something called Service Fabric. CRP is an example of a microservice-based service. It consists of more than 7 microservices. You can see just a handful of them here. Repository for our images and extensions, patch management, orchestrator, disk manager for deploying managed disks, and the VM manager, of course, itself, which is responsible for talking to compute stamps to go deploy VMs within clusters. And it does kind of region-wide allocation as it gives requests to the compute stamp that a VM should land on, orchestrating, of course, with network resource provider to rendezvous, like I talked about before, on the node so that the virtual machine's network resources end up being programmed on the same server that the virtual machine lands on. That's a very high-level look at compute resource provider. Now, I mentioned that compute resource provider is built on a microservices platform we've been working on since 2007, actually, called Service Fabric. So Service Fabric was designed with microservices in mind and a declarative model long before we saw the rise of these other orchestrators. It went into production for the first time in Azure as the foundation underneath Azure Database. And it's got a number of unique characteristics. It supports what we call stateful microservices, meaning you can store state directly on the servers. It's state aware and maintains high availability and durability of that state. In the case of Azure Database, each database you create is backed by 3 or 4 Service Fabric, what we call replicas or microservice instances on different servers in different racks in our data center. And that means that if a rack fails, you still have access, durable access, write access to your database. 4 is for the premium databases. The way that a developer approaches Service Fabric for that state replication is basically as a one-box programming model. I just worry about writing my state to my local store, and I tell Service Fabric I need to replicate something. Service Fabric takes care of where are the secondaries, leadership election, catching those secondaries up with the primary in the case of a failover or a restart. All of that magic Service Fabric takes care of. So more and more of Azure and Microsoft is built on top of Service Fabric. CRP, NRP, SRP, all built on Service Fabric. Intune's built on Service Fabric. Service Bus, Event Hubs, Event Grid, Power BI, all built on top of Service Fabric. And the list goes on. Cortana is built on Service Fabric. The list goes on and on and on. Service Fabric, more recently, in fact, this week at Build, we're GAing Service Fabric for Linux. It started out as Windows only, and it started out as something that you deployed on your servers yourself. A couple years ago, we launched as a preview Service Fabric as a service in Azure, which is now GA, where you can go and we stand up the Service Fabric cluster for you, and we manage the updates to the Service Fabric infrastructure for you. About a year and a half ago, we announced that we were porting Service Fabric to Linux. That port was complete, and now it's GA'd today, or yesterday. So you now, and as part of that, this evolution of microservices, we also released support for containers, both on Windows for Service Fabric, Windows Server containers, as well as Hyper-V containers, and now on Linux, of course, Docker containers. Just to show you how powerful Service Fabric is, I'm going to set what we believe is a world record in front of you for container deployment. What I'm going to do is deploy 1 million containers in front of you live onto a Service Fabric cluster, and we'll see how long it takes. And hopefully not too long. So here's a look at the Service Fabric Explorer for this cluster. You can see that this cluster consists of a little over 3,500 VMs running in public Azure. There's 3,500 VMs where we're going to deploy those containers. There's 9 VMs where we're running the Service Fabric controllers themselves. And you can see that there's 3,500 replicas already there, because on each VM, we've got something that is counting how many containers land on that VM. And then there's another extra microservice that is aggregating the answers from all of them, and then has a web API that we're going to query from another app so we can watch in real time the containers come up. Important to note about this demonstration is that we're measuring the time it takes from me pressing go to the time 1 million containers are up and actually running. Not just, oh, Service Fabric got them and it's deploying them. So let's go ahead and go. So here's the PowerShell script that's going to launch this. And I'm going to switch over to another UX here in a second. How many people have heard of the Cassini probe? Raise your hands. Cassini? Any space people, fans in here? Just a few. Cassini is the probe that went to Saturn and just basically committed suicide a few weeks ago by plunging into Saturn and sending, well, that's not what we're supposed to see. Hold on. There we go. We're already at 42,000 containers. Now, as these containers get created, this animation is going to create these little particles circling Saturn. Each one of those particles represents 10 containers. When this is done, we're going to have 100,000 particles. So this is an homage to Cassini. And I thought it'd be more fun to watch this than just a number. But, so I don't know if any of you have been counting or looking at your watch from when I pressed go. We're going to see, and I'll tell you approximately what this is. We're up to 370,000. So there's been one other test we know of in public that deployed 1 million containers. It was on to a larger number of machines, and at 5 minutes, they had them scheduled but not running yet. So this is from 0 to running on 3,500 machines. We're at 662,000, so just a little bit more to go. And of course, if I didn't make it clear, these are Linux VMs running Docker containers on them. So each one of these is a Docker container. Okay, 857,000, just a little more. In fact, we're going to go blowing a little bit past 1 million because we really want to make sure we had the record of 1 million. So it's like Price is Right. Now somebody can't just do 1,000,001 and beat what I'm going to show you. There we go, 1,024,000. And that, I don't know if you timed it, but every run that we've been doing on this is about 1 minute 45 seconds. So I think that was about the same amount of time, about 1 minute and 45 seconds to get to 1 million containers. So that shows you the kind of scale and robustness that we have with Service Fabric. So let's talk a little bit about now Confidential computing. This is a new service that we've got that is aimed at protecting your confidential data. So some of the concerns we've heard from customers with very sensitive data, for example, core IP or your customer's data or health data or financial data is, I put it in the public cloud. Well, what if there's a malicious insider in Azure? They might get it and leak it all over the web. Or what if there's a breach of your multi-tenant boundary and malware or hacker gets in and gets access to my data? Or what if some government agency comes and compels you to give them our data without our knowledge? This confidential computing initiative, which we announced a couple weeks ago, is aimed at addressing all of those. You can take Microsoft out of the trust equation when you deploy your code and data into the cloud by leveraging what are called trusted execution environments, or enclaves, TEEs. The idea behind a TEE is that it's effectively a black box where you can stick code into it and stick data into it and then ask it what it's running. And it has to be able to prove to you what it's running. There's several TEEs we're launching with. One of them is Virtual Secure Mode, which is built into Hyper-V, where Hyper-V protects a little black box such that even an administrator on the server can't get access. But the other TEE we're launching with, is called SGX, Software Guard Extensions, which Intel pioneered and came out to market with about 2 years ago. We've been working very closely with Intel to get these SGX-enabled servers into our data center, the first public cloud to do it. And that allows you to get hardware, basically encryption in use, where even somebody that sits a logic analyzer up to the server cannot see what's going on inside your enclave. And SGX will attest to the fact from the processor that it is running inside the enclave a specific piece of code and configuration, so that you can go and verify by talking to the enclave and say, are you running something I trust? It can prove to you that according to the CPU, it is, and then you can release secrets to it. And then, given those secrets, it can do computation on data that's encrypted that it loads in and decrypts using those keys, and where it's protected from these kinds of threats. This confidential computing initiative is something where we've been working on it for many years with MSR on compiler technologies to prevent side channel leaks. We've also been exploring different kinds of services and how they could take advantage of them, from big data MapReduce scenarios to SQL Server. And what we're doing, how many people have heard of SQL Azure or SQL Always Encrypted feature in SQL, which lets you encrypt columns with an encryption key that you possess. Now, the problem with that is that SQL queries on the back end can only do very primitive types of operations on those encrypted columns. Basically, depending on if you've got a deterministic encryption algorithm, it can see if 2 rows are equivalent. And that's about it. You can't do greater than, less than, and other kinds of sophisticated computations on it. But by taking advantage of confidential computing, SQL is going to be introducing what they call always encrypted vNext, which will let you encrypt columns, have the encryption keys be protected with SGX enclaves, and then be able to do rich queries in the cloud on encrypted data in your database. And I've got a demo of that. Preview showing you what this is going to look like. So I'm going to log here into an SGX server. And what I've got here is a query of my database. I'm going to execute it, and I've got 2 columns in here that I've encrypted in the public cloud, the social security number and the salary. So what comes back from the SQL query is just encrypted data. So I don't have access to those keys. I'm not going to be able to see them. And if you take a look at how I created this database, here's where I created it. And you can see that I took the salary and I encrypted it here with a column encryption key. This column encryption key is protected with the master key in Azure Key Vault. I've got access to the master key using Key Vault Access. I can decrypt the column encryption key. I can have SQL prove to me that it is running software that I trust. And then I can hand it the column encryption key over a secured encrypted channel that only the enclave has access to, so that it can perform those computations. So let's go see what that looks like. I've got here an example client app. And the nice thing about this, by the way, is that you don't need to modify the client app in any way. ADO.NET has will have built-in support for this, so it's completely transparent to a web application like this. This is a Contoso HR app that's working against that database. And then I've got the SQL profiler over here to watch what happens underneath the hood. I'm going to select employees, and what that does is does a SQL query to go get the list of employees. And you can see in this list, I get back the social security numbers because I'm authorized to see them. I know that column encryption key. I've gotten it out of Key Vault. I can do searches, rich searches, like I can search for a particular social security number. I can do comparisons, greater than, less thans. I want to see salaries that are within some range. That computation's actually happening on the back end in that enclave, in the enclave, so that that confidential data never escapes. It's completely protected by SGX. And if I go to the SQL query profiler and go to that last line, you can see that that query, what I did was pass in to a stored proc encrypted search patterns that are going to be used to decrypt those columns inside the query engine so that SQL can actually perform those queries on my behalf and return the results. So this is taking cybersecurity to a next level. We believe that actually we've launched a new era in cybersecurity with confidential computing. And if you're interested, we've got an early access preview going. So there's a form online you can go fill out to get access to the early access preview. We'd like to work on it, especially we're looking for customers with lots of different scenarios to work with to make sure that when we launch this thing, it meets everybody's needs. And that'll include tooling support in Visual Studio, enclave support for Linux, enclave support for Windows, virtual secure mode support for Windows as well. Okay, let's take a look at storage. Now, one of the aspects of storage is storage requirements are exploding, as you know. So we're generating so much data. We want to keep more data. And so we're moving from petabyte size customers now. We're seeing customers that want to store exabytes of data on the order of. We're seeing systems that need to go from supporting exabytes to zettabytes of data. One of the things that we've been focused on is reducing the cost of storage over time, and this is a normalized to our Gen 0 storage server, the cost of a byte as we've gone through our storage server generations. And you can see that on Gen 4, we're down to 0.005, the cost of a byte that we had on a Gen 0 system. So massive reduction in cost by more efficient software design and more efficient server design to support storage. We see that these kinds of improvements, the opportunity to improve on cost per byte for both hard disks as well as tape, is got a lot of runway left in it. About 80% improvement left through 2027, we predict. About 95% improvement in tape. And I'll talk about why we're talking about tape in a second. Flash looks like it's about capped at 80%. Now, even with these improvements, we expect to see the ratio of price per byte between these different technologies to be about the same. 10-to-1 flash to hard disk and 10-to-1 hard disk to tape. If you take a look at what we're doing to improve technologies in the cloud, you can see here the latencies as well as the data temperature. So you want flash. Flash is going to be more expensive, aimed at hot data. Hard disks, a little cooler, a little less expensive. And then finally tape, very cold, archival, and takes hours to access it. We're working on bringing down flash storage through deploying RDMA into our data centers between our compute servers and our storage servers, down to low hundreds of microseconds. We're also deploying, and we announced a preview of Azure archival storage for blobs just a few weeks ago. We're deploying tape units. Here's a picture of a tape unit that we've deployed to support this archival storage. Now, what you're looking at here is each one of those boxes supports up to 72 tape drives, and stores 12,000 cartridges of tape. Has 1 or 2 robots in each one, and we can put up to 16 of them side by side for expansion. Now, on each side of it, we've got service frames so that operator can come and service it. But we're not stopping there with that technology. We're actually working on other technologies to fill in gaps in the latency versus data temperature graph. We've been working with Microsoft Research on something called Pelican for several years, and this is also what we're going to be rolling out as for archival storage in regions that aren't big enough to support tape libraries, but give us pretty good cost efficiency. Pelican effectively is one giant rack storage server. It's got some compute servers in it, a couple of them for high availability, and then a PCI Express fabric stretched over the whole rack. What makes this extremely efficient? Now, if you powered all these hard disks, you can see that there's over 1,100 hard disks. This thing can store a total of over 11 petabytes raw. If you had all those hard disks running at the same time, this thing would be a massive, incredible power draw and cost a lot of money to operate. So the Pelican design is such that only some of the disks can be powered up at any given point in time. So there's a scheduler inside this compute servers that will figure out, oh, this is the data access I need. Let me go and make sure I orchestrate this so that I don't have more than the limit of disks active at any one point in time, and that keeps the power draw down, which keeps the cost per byte down for us. Here's a picture of Pelican, or actual Pelican device, and that's a Gen 3 storage device. You can see all those are disks inside the Gen 3 storage device, and then the full Pelican rack of disks there on the right side. We're also working on other storage technologies as well. So we're working with University of Southampton in England on a project we call Project Silica. It is storing data on glass. Now, why have you never heard of data on glass? Glass has some really cool characteristics. One is it lasts literally forever. It's going to outlast us. It's going to outlast the Earth. So this is, you want durable long-term storage. Glass is going to give it to you. The other benefit of glass is that you don't need a special reader to read it. If you can get a laser, you know how to read it. So unlike other technologies like DVDs, and how many people have a Betamax? Can you read a Betamax anymore? That's kind of lost data at that point. But with glass, you can always get a laser and figure out how to read it. So it's got these benefits, but why haven't we seen anybody get storage onto glass? The answer is that up to now, nobody's figured out how to pulse lasers quickly enough to both encode data and not break the glass. You've got to have pulses that are extremely short. Pulses, the same kind of pulses when you have laser surgery on your eye, that kind of pulse. That pulse is femtosecond. How long is a femtosecond? It's not long at all, you can see there. I don't know how long that is. Now I've actually got an example of this right here. Encoded on this, and that's a little close-up of it, that's 25 microns. We call these things voxels. It's multiple layers are encoded. This is 5 layers deep into the glass. And there's 3 bits that we can encode in this particular rev of the technology. There's a little tiny piece that's been written inside this glass. That's 50 terabytes of storage right there, which is enough for 2 Libraries of Congress. And here's how you can. This is how we encode the voxels. So we use the retardance of laser and polarization angle to get those 8 bits, and you can see each of those 8 bits colored there as the retardance, 2 levels of retardance and 4 levels of polarization. And then here's a screen, kind of a image capture of our reader. There's the reader at Microsoft Research in Cambridge, England, and you can see the lasers pulsing and reading the voxels off that little die that I just showed you. But we're also working on even more breakthrough storage technologies. This project is called Palix, and it's a joint project between University of Washington and Microsoft, which is aimed at using DNA to store data. DNA is 1,000 times denser than tape, and it also lives way longer, where it lives longer than tape. You see 2,000 years without having to be rewritten. Now, the idea behind DNA encoding is you take some bits, you encode it into DNA sequences, then you write it to a DNA molecule, and then you can randomly access it, get this gene, basically do gene sequencing, and then you can read the data and the specific genes map to specific bits, and then you can reconstruct the data. This thing promises to be another quantum breakthrough or DNA breakthrough. There's 10 terabytes right at the tip of that little there, 10 terabytes of data encoded in DNA. This, just to show you, that box right there, that will be able to store 1 zettabyte of data. That one chassis right there in DNA. So that's a look at DNA. All right, I've got a final section now inside the Azure operating system. The Azure, oh, by the way, there's just a day coming when Maury Povich is going to have to do DNA tests to see if your server admin backed up the data. All right, let's take a look inside the Azure operating system. We run stock Windows Server. In fact, we've been rolling out Windows Server 2016 as our virtualization host. Now, we do some custom things to it to really optimize it as a compute OS for a hyperscale cloud. One is that we have no 32-bit code in it. We have no managed code in it. We remove all the language packs out of it. So we strip it down to be very small. It's server core. We disable all unused drivers, the print spool, and everything else. That reduces both the surface from a reliability perspective and from an attack perspective. And then we also have the minimal set of server rules on it. One of the challenges we face, as with any piece of software, is updating this. There's a unique challenge when it comes to updating the Azure OS and the hypervisor, and that's that we've got your VMs running on top of it. And those of you that have been with us for a while know that sometimes when we have major updates to the operating system, we require a reboot of your VMs because we need to reboot the servers underneath. But we've been working on a number of technologies. We are optimistic that over time we will completely eliminate reboots, and I'm going to show you some of those technologies, talk about them, and then show you them in action. Many of these technologies we've already got in production, and we're just working on optimizing them to the point where we can eliminate reboots. One of them is called VMFoo. VMFoo stands for Virtual Machine Preserving Host Update. The idea behind VMFoo is that the server's running along. We want to replace host OS A with a new OS. So we freeze the VMs, shut down the OS, reboot the OS into the new version, and then resume the VMs. So the VMs are paused for a short period of time while we do this. Our goal is to be extremely short. Our goal is to be under 9 seconds, which is the TCP timeout in a reliable network, or reliable LAN. But we developed other technologies. That's the basic one there at the bottom. We've got something we call VMFoo Lite. We've got something called VMFoo Ultralight. So VMFoo, with kernel soft reboot, you can replace the whole operating system, the hypervisor and everything. With VMFoo Lite, we can replace the entire virtualization stack, except for the hypervisor itself. So everything else. In fact, most of the reliability and security issues that we find are in those parts of the virtualization stack, the networking stack, the storage stack, the virtual machine manager, those components. VMFoo Ultralight can replace almost everything except for one component of the virtualization stack, the one that manages the core state of the virtual machines. But everything else can be replaced with VMFoo Ultralight. And then we also have an investment in hot patching that I'll talk about. But let me show you what VMFoo Lite and Ultralight look like by doing them on a live VM. So I've got here a virtual machine. I'm logged into an Azure server, host server. That's where the PowerShell window is running. On the right side of this window, that's a virtual machine. I've connected to that virtual machine locally, so you can see the GUI on it. And I've got this PowerShell script that's going to measure if it sees any gap in time as it's polling time that's more than a few milliseconds, 10 milliseconds, it's going to report what blackout is. So it's going to detect any kind of hiccups that it will occur as that virtual machine is getting paused for one of these operations underneath. And what I'm going to do is run this demo. The first thing this demo is going to do is a VMFoo Ultralight. So this is going to replace the entire virtualization stack except for the hypervisor out from underneath that virtual machine. So if we wanted to do a reliability, performance update, or feature update, this is what you would see. So get ready. Here we go. So we had a blackout of about 3 seconds, replacing the whole virtualization stack. Now, that's a VMFoo Lite. Now, VMFoo Ultralight, which addresses almost all the same kinds of fixes, in fact, all the ones we've done in production, let's see what that looks like. So get ready. There. Now, that's pretty good, but our goal is actually to not disrupt virtual machines at all when we need to do updates. Some of you might be aware that Windows at one point had invested in hot patching technology, and then kind of didn't pursue it, because one of the challenges with Windows updating is that on Patch Tuesday there was always some component that needed a reboot that couldn't be hot patched. Now, hot patching is not a universal panacea. There's many security and reliability fixes that simply cannot be hot patched by their very nature. But it does apply to many, however. But if you just have one component that can't be hot patched, then you're needing to reboot your Windows system. Now, the fact is that we're not doing Patch Tuesdays in Azure. We're basically rolling out software continuously. And so if we need a fix, we want to roll it out. Especially a security fix, we want to roll it out as quickly as we can. And if it can be hot patched, that's what we do. The idea behind hot patching is that you've got some code that's got a problem in it, and you patch the entry point to that code to point at some good code. So when somebody calls a bad function, they get redirected to the good code, and then they return back through as if they executed the bad code, but it was really skipped. So it's basically overlaying code on top of one another. And typically, when you want to hot patch a vulnerability, there's multiple places in the code flow that need to be addressed and changed. So a hot patch oftentimes touches multiple functions at the same time. And one of the things that our hot patching support does is does an atomic update of the code, verifies that it's safely applied, and then lets the hot patch go through. The processors are paused during this point in time so that we ensure that nothing is going to be in this weird intermediate state or get through the partly hot patched system. We've used hot patching in production over 50 times now. So it's really saved our availability numbers because we haven't had to even do a VMFoo Lite or Ultralight. We're basically able to do it completely transparently. And I've got a demonstration of what hot patching looks like to show you just how transparent it is. Now, in this little demonstration, the scenario is, and we've created this by taking the virtualization driver. This is the unaccelerated one. But just to give you an idea of what hot patching can do, we've got two VMs here running in Azure, talking to each other. Well, I'm going to make them talk to each other. And the driver that they've got, there's a receiver, and here's the sender. The driver they've got has a bug where it is only able to, actually this is accelerated networking. There's a piece of the stack that this passes through. You can see it's only able to achieve about 6 gigabits per second. We should be seeing way higher than that. So the idea is that we've got a bug that we need to go fix. We want to do it with minimal disruption. If I take a look at the hot patch status of this server, so let me switch to this is the console on the server. I do a patch query. These are the patch management tools that we've created. And by the way, we support, this is integrated into our version of Visual Studio, so we can do hot patching on the code inside of Visual Studio. You can see that I've got that VM switch, which is the one that has the problems in it, loaded, but no hot patch is applied to it. What I'm going to do is apply the hot patch, and I want to do it right here so you can see what happens to the network bandwidth as I apply that patch. So ready? Watch that receive number. Here I go, 1, 2, 3. So what that just did, you can see all the patch locations that we had to go touch to fix that bad code. But we were able to do it with 0 downtime, on the fly, and get that addressed. So that's an example of how we're pushing these kinds of technologies to get rid of any VM impacting updates. So that brings me to the conclusion of the session. I hope you found it interesting. I hope you got an idea or flavor for the kinds of innovations that we're driving across network, compute, storage, server design, and even maintenance of the operating system across the platform. This is something that is completely a work in progress. I'll likely, if I get good feedback, do this session every Ignite, and you're going to see, of course, the latest wave, because we're moving really quickly. In fact, many of the things that you'll see here might even be in production, so I won't even talk about them anymore, and I'll talk about the next wave of innovation that we've got going in the cloud. But one of the things I hope I conveyed to you is that the kinds of innovation that are happening in data center software and hardware, with our focus on it across all of our teams, is something that is pushing the envelope way faster than what we've seen over the last 10 years. Now you're seeing this acceleration of innovation across the whole stack from Azure. So with that, I want to, again, thank you. Hope you have a great Ignite. By the way, I'm doing a book signing with Aaron Margosis tomorrow at 12:30 if you want to come by and buy Windows Internals or one of my novels or SysInternals Administrator, Troubleshooting with SysInternals. I hope to see you there. And Casey then explained tomorrow afternoon. So hope you have a great Ignite. Hope you had a great session, and hope to see you tomorrow. Thanks.